Have you ever wondered why the ringing of a bell or the note from a guitar string fades away gradually instead of abruptly stopping? Welcome to the intriguing world of damped oscillations. In the simplest terms, damped oscillations refer to a periodic motion where the amplitude or the size of the oscillations gradually decreases until it eventually stops. The culprit behind this is a force known as the damping force, which opposes the motion of the system and gradually eats away at its energy. This is a concept deeply rooted in the fundamental principle of energy conservation. In an ideal world, the total energy in a system would always stay the same. But we don't live in an ideal world. Instead, we live in a world where forces like friction and radiation siphon off energy from the system, turning it into thermal energy. This energy transfer is what causes the system's oscillatory amplitude to reduce gradually. Damped oscillations are everywhere, from the mechanical vibrations of a guitar string to the oscillations in voltage or current in electrical circuits with resistors, to the simple pendulum swinging back and forth. All these are examples of damped oscillations. Depending on the strength of the damping force and the system's characteristics, there are three main types of damped oscillations. First, there are underdamped oscillations, characterized by periodic oscillations with a gradually decreasing amplitude. This is the most common type, and it's what you see when you watch a pendulum swing. Next, we have overdamped oscillations. Here, the damping force is strong enough to prevent oscillations entirely. Instead, the system returns to its equilibrium position without any back and forth movement. This type of damping is often desirable in engineering applications to minimize unwanted vibrations. Finally, we have critically damped oscillations. In these systems, the return to equilibrium is as quick as possible with no oscillations. This type is ideal for applications requiring a rapid and smooth transition to equilibrium, such as the shock absorbers in a car. To analyze damped oscillations, we use differential equations that incorporate the damping force. This force usually involves a coefficient known as the damping factor, which quantifies the strength of the damping effect. The higher the damping factor, the quicker the decay of the oscillation's amplitude. By understanding damped oscillations and their various forms, we can better model and analyze a range of physical phenomena. This knowledge is crucial in numerous real-world applications, from designing stable structures to optimizing control systems. So the next time you notice the gradual fading of a bell's ring or a guitar note, you'll know there's more to it than meets the eye. It's the fascinating physics of damped oscillations at work.